Let's kick things off by exploring the concept of momentum in physics. Momentum is a fundamental property of moving objects, describing how much motion they carry. It's not just about speed, it's also about mass. The more massive an object and the faster it moves, the greater its momentum. Imagine a bowling ball rolling down a lane versus a tennis ball at the same speed. The bowling ball has much more momentum. This concept helps us understand why some objects are harder to stop than others. As we dive deeper, you'll see how momentum connects to everyday experiences and scientific principles alike. Now that we know what momentum is, let's look at how it's calculated. In physics, momentum is represented by the symbol p and is calculated as the product of an object's mass and its velocity. The formula is simple: p equals m times v. Here, m stands for mass and v stands for velocity. This means that both how heavy something is and how fast it's moving determine its momentum. This formula is the foundation for understanding how momentum works in all sorts of situations, from sports to car crashes. Let's focus on mass. Mass is a measure of how much matter an object contains. When it comes to momentum, mass plays a crucial role. If two objects move at the same speed, the one with more mass will have more momentum. Think about a truck and a bicycle moving side by side at the same speed. The truck, being much heavier, has far more momentum. This is why stopping a truck takes much more effort than stopping a bicycle, even if they're moving equally fast. Velocity, or the speed and direction of an object, is the other key factor in momentum. If two objects have the same mass, the one moving faster will have more momentum. For example, a baseball thrown at high speed has more momentum than one tossed gently. This is why fast-moving objects can cause more impact or damage when they collide with something else. Velocity amplifies the effect of mass in the momentum equation. See momentum in real life. Picture a soccer player kicking a ball. The ball's momentum depends on its mass and how fast it's kicked. If the player kicks harder, the ball moves faster, increasing its momentum. This is why powerful kicks send the ball flying further down the field. Momentum is at play every time you see objects in motion, from cars on the highway to athletes in action. One of the most important principles in physics is the conservation of momentum. This law states that in a closed system where no external forces act, the total momentum remains constant. For example, when two ice skaters push off from each other, they move in opposite directions, but the total momentum before and after they push remains the same. This principle helps scientists predict the outcomes of collisions and other interactions. Collisions are a classic example of momentum in action. When two cars crash, their combined momentum before the collision equals their combined momentum after, assuming no outside forces like friction. This is why car crash investigators use momentum calculations to reconstruct accidents. The way momentum is shared or transferred during a collision depends on the masses and velocities of the objects involved. In an elastic collision, both momentum and kinetic energy are conserved. Think of two billiard balls striking each other on a pool table. After they collide, they bounce away without losing speed or energy. Elastic collisions are idealized, but they help us understand how momentum and energy interact in real-world scenarios, especially in physics experiments and games. Contrast, inelastic collisions occur when objects stick together after colliding, and some kinetic energy is lost, usually as heat or sound. For example, when two cars crash and crumple together, that's an inelastic collision. Momentum is still conserved, but the objects don't bounce apart. Understanding inelastic collisions is crucial for safety engineering and accident analysis. Pulse is a related concept that describes the change in momentum. It's the result of a force acting on an object over a period of time. For example, when you hit a baseball with a bat, the force of the bat over the short contact time changes the ball's momentum. The greater the force or the longer it's applied, the bigger the change in momentum. This is why follow-through is important in sports like golf or tennis. Momentum isn't just for scientists, it's everywhere in daily life. When you ride a bike and suddenly brake, you feel your body lurch forward because your momentum wants to keep you moving. The same principle applies when a bus stops suddenly and passengers sway. Understanding momentum helps explain these common experiences and can even help you stay safer. Athletes use momentum to their advantage all the time. In football, a running back lowers their shoulder to gain extra yards, using their mass and speed to push through defenders. In basketball, players use momentum to drive toward the basket. Coaches and players study momentum to improve performance and reduce injuries. Vehicles are a perfect example of momentum in action. The heavier and faster a car or truck moves, the more momentum it has. That's why large trucks need more distance to stop than small cars. Engineers design brakes and safety features with momentum in mind, ensuring that vehicles can stop safely even at high speeds. Momentum isn't limited to Earth. In space, momentum plays a vital role in how spacecraft move and interact. When astronauts push off from the space station, they float away due to the conservation of momentum. Space missions rely on precise momentum calculations to navigate and dock with other spacecraft. Momentum isn't just about straight-line motion. Angular momentum describes the momentum of rotating objects. Think of a spinning figure skater. When they pull their arms in, they spin faster. That's because their angular momentum is conserved. This principle is important in everything from spinning wheels to planetary orbits. Rotational motion is everywhere, from bicycle wheels to the Earth spinning on its axis. The same principles of momentum apply, but in a circular path. Engineers and scientists use angular momentum to design everything from amusement park rides to satellites. Understanding rotational motion helps us make sense of the world spinning and turning objects. Safety devices like airbags and seatbelts are designed with momentum in mind. In a crash, these devices help reduce the force on passengers by increasing the time over which momentum changes. This reduces injuries and saves lives. Understanding momentum allows engineers to create safer vehicles and equipment for everyone. Momentum isn't just a human-made concept, it's found in nature too. Animals use momentum to leap, run, and hunt. For example, a cheetah builds up momentum to chase down prey, while birds use momentum to glide through the air. Nature's creatures are experts at using momentum to survive and thrive. Sports equipment is designed to maximize or control momentum. Tennis rackets, golf clubs, and baseball bats are engineered to transfer as much momentum as possible to the ball. The design, weight, and material all play a role in how momentum is transferred, helping athletes achieve better performance. Engineers use momentum principles to design everything from bridges to roller coasters. By understanding how forces and motion interact, they can create structures that withstand impacts and move safely. Momentum calculations are essential for building safe, reliable, and efficient machines and structures. Accident investigators rely on momentum to analyze crashes and falls. By calculating the momentum before and after an incident, they can determine causes and improve safety measures. This science helps prevent future accidents and makes our world safer. Modern technology, from smartphones to rockets, relies on momentum principles. Devices that move or launch use momentum calculations to function properly. Whether it's a robotic arm or a drone, engineers must account for momentum to ensure smooth and safe operation. Entertainment industries use momentum in everything from movie stunts to theme park rides. Stunt coordinators calculate momentum to keep actors safe during action scenes. Ride designers use momentum to create thrilling experiences while maintaining safety standards. Science experiments often demonstrate momentum in action. From rolling marbles to launching rockets, students and scientists observe how mass and velocity affect motion. These hands-on activities make the concept of momentum clear and memorable. Momentum and energy are closely related in physics. While momentum measures motion, kinetic energy measures the energy of that motion. Both depend on mass and velocity, but they're used in different ways to analyze movement and collisions. Understanding both concepts gives a fuller picture of how things move. Weather systems, like hurricanes and tornadoes, involve massive amounts of momentum. The swirling winds carry momentum that drives their movement and power. Meteorologists study momentum to predict how storms will develop and move, helping communities prepare for severe weather. Water in motion, like rivers and waves, demonstrates momentum on a grand scale. The mass and speed of moving water can shape landscapes and power hydroelectric plants. Understanding water's momentum is essential for engineers and environmental scientists alike. Pilots and aerospace engineers must account for momentum when designing and flying aircraft. The mass and speed of a plane determine how much runway is needed for takeoff and landing. Momentum calculations ensure safe and efficient flight operations. Medical professionals use momentum concepts in fields like physical therapy and sports medicine. Understanding how the body moves and absorbs impacts helps prevent injuries and improve rehabilitation. Momentum principles guide safe exercise and recovery techniques. Robots that move or manipulate objects must account for momentum to operate safely and efficiently. Engineers program robots to control their speed and force, ensuring they don't cause damage or lose balance. Momentum calculations are key to modern robotics. Construction workers and engineers use momentum to safely move heavy materials and operate machinery. Cranes, bulldozers, and other equipment rely on momentum principles to lift, swing, and place objects precisely. Safety protocols are based on understanding how momentum affects moving loads. Artists sometimes use the concept of momentum in their work, especially in kinetic art where objects move or spin. The interplay of mass and motion creates dynamic sculptures and installations. Momentum brings art to life in unexpected ways. Video game developers use momentum to create realistic movement and physics in games. Characters, vehicles, and objects behave according to the same rules as in real life, making gameplay more immersive and challenging. Momentum adds excitement and realism to virtual worlds. Teachers use momentum demonstrations to engage students and make physics fun. Rolling balls, swinging pendulums, and other hands-on activities help students visualize and understand momentum. These lessons inspire curiosity and a love for science. The study of momentum dates back centuries, with scientists like Isaac Newton and René Descartes laying the groundwork. Their discoveries helped shape our understanding of motion and paved the way for modern physics. Momentum remains a cornerstone of scientific progress. Factories and industrial machines use momentum to move products efficiently. Conveyor belts, robotic arms, and assembly lines all rely on momentum principles to keep things moving smoothly. Understanding momentum boosts productivity and safety in manufacturing. Trains, ships, and airplanes all depend on momentum for efficient travel. The mass and speed of these vehicles determine how much energy is needed to start, stop, or change direction. Transportation engineers use momentum calculations to design safer and more efficient systems. Wind turbines and hydroelectric plants harness the momentum of moving air and water to generate electricity. The mass and speed of these natural forces are converted into energy, powering homes and businesses. Momentum is at the heart of many renewable energy solutions. Even in finance, the term momentum is used to describe the tendency of investments to keep moving in the same direction. While it's a metaphor here, the idea comes from physics. Objects in motion tend to stay in motion. This concept helps investors understand trends and market behavior. Momentum can also describe the flow of ideas and communication. In group projects or meetings, once a discussion gains momentum, it's easier to keep moving forward. This social momentum helps teams achieve goals and solve problems more efficiently. Cultural movements often build momentum as more people join and support a cause. This collective energy can lead to significant social change. The idea of momentum helps explain how small actions can grow into powerful movements. Learning new skills often requires building momentum. As you practice and improve, progress becomes easier and faster. This positive feedback loop is similar to how objects in motion tend to stay in motion, making learning more effective over time. Personal growth, like physical momentum, often starts slow but builds over time. Setting goals and taking small steps creates momentum, making it easier to achieve bigger things. This principle applies to habits, fitness, and self-improvement. Innovation often relies on momentum. Once a new idea gains traction, it can lead to rapid progress and breakthroughs. Companies and inventors use this momentum to stay ahead and drive change in their industries. Momentum is a powerful force both in physics and in life. It explains how objects move, how energy is transferred, and how progress is made. By understanding and harnessing momentum, we can solve problems, create new technologies, and improve our world. Whether you're studying science or striving for personal growth, momentum is a key to success.